All right. So we got streaming done. It started already. So this is going to be your lab activity for today, which is our first attempt to understand how the processor works. Okay. So the questions does require you to use Logisim and also the processor things that we used last time in the previous lab. So you might want to put Logisim, the processor file, and the other two files onto a thumb drive. So this way, when you get to the lab, you just plug in a thumb drive and everything is good to go. Okay? If you have your own laptop computer, obviously that does not apply to you because you can just save it locally to your computer. So what we'll do today in lab is really to look into specific instructions like the LD or the load instruction, which reads 1 byte from RAM and put it into a register. Okay? So what we'll do during the lecture is really just looking into the processor and find ourselves a path to do that. Okay? We want to read a location in RAM and put it into one of the registers. If I do not name a register, if I just say a register, that means it is one of the 4 registers in the register bank. They are named register A, B, C, and D. Okay? The other registers, there are many other registers in the processor, but each one has a very specific name. Like the program counter is PC. The microcode pointer is the microcode pointer, and so on and so forth. So if it is just a register, it is referring to one of the 4 what we call general purpose registers in the register bank. So do we have any questions at this point? Yes? Yes, I confirmed that earlier. Doesn't hurt to double check, right? So, and it's the last one here. So we are indeed streaming and audio is good. All right, so what we'll do now is we're just going to open up Logisim, and I have to go find, these are not the ones I want. So let's get rid of these. They're just for setting up the monitor. Every time I plug in an external monitor, it pops up one of those, and I never bother to close them, so that's why there are so many of those. All right, so let's go ahead and see if I have a terminal running. Yep, we do. And we'll go ahead and start Logisim. And remember, in Logisim, the file that we need now is going to be the one called processor. And I'm not sure whether this folder has it or do I have to go back to my other folders. Yep, it does have it here, still here. So processor 0003 is the one that we need to use for this semester. So it has a sequence number because I keep changing it. So the best way to keep track of which one I'm going to use is to use a number. So that's why we got a revision number. Okay, so this is the processor, and we want to move a byte. We want to copy a byte from RAM. Let me zoom out so that you can see better which component is which component. So what we want to do is we want to copy a byte from a location in RAM, which is this component here, to one of the registers inside the register bank. The register bank is all the way here. Okay? So the direction is we want the output of the RAM component to go to the input part of the register bank module so that we can update one register. So if that is what you're required to do, okay, let's not look into the instructions. How would you figure this out? We know the 2 components that are needed. So now the question is, how do we coordinate everything else so that we can accomplish what I just mentioned? So where do we start? There are several places where we can start, but how would you start this process? So I'm going to put up a notepad here, just so that I can take note of what we're going to do here. Okay, so the task that we need to do is to read a byte from RAM and update a register in the register bank, okay? And let's be more specific about this. So the next question is, how do we specify that location in RAM? Wouldn't that be a good question to ask? Because if you're reading a location, if you're reading a byte from RAM, then you have to ask yourself, which byte are we reading? Because how many bytes do we have in this particular RAM module? It has an 8-bit address bus, so it can address how many locations? 2 to the power of 8, which is 256 locations. So I have to choose one of the 256 locations. So now we also need to say, but how do we specify the location in RAM to read from? So here is what we want to do. So I'm going to give you exactly what I want to do. So I'm going to say use register B to specify which location in RAM to read, and update register D with the content in RAM, okay, with the addressed content in RAM. So this is specifically how I want to do it. How would you get started with this whole process? Just given these two sentences, how are you going to get started?
You look for an instruction that uses B and D.
Well, we're not even talking about instructions. I'm talking about, if you have control over all of these things, and there's no, component down there anymore, okay, and you are Sir Topham Hatt, okay, the controller, how would you configure the train tracks so that you have, you can perform that operation? That's the question. So we are doing this completely manually, okay? Yep, go ahead. RAM select. Okay, so someone says RAM select. Yes, so we do need to access RAM. Okay, so let's write down what we need to do. I'm unfortunately I just cycled through the whole thing. So RAM select has to be a 0 or 1. Has to be a 1. Okay, very good. Okay, what else do we need to do about the RAM module when we are reading from RAM? Yep.
The load needs to be 1.
RAM load is 1. Very good. What else? Anything else?
You need to specify the location of the address.
Okay, so we need to specify the location. Very good. Okay, so that's a very good observation. So we need to specify the address. Of the two ports, A and D, which one specifies the address? A. Why did you think of A? After all, D is the second letter of address. Okay, so we focus on this and go like, okay, something needs to specify, the address that where we want to access in RAM. But this actually goes to a it's not a dead end, but it comes to a point where, what do we do? What do we do now? It comes to a MUX. It's a multiplexer. So tell me what a multiplexer does from the previous class. It selects one of several.
It kind of acts like a switch.
It is a switch. So one side has multiple and the other side only has one. So which side is input and which side is output? Multiple in, one out. Very good. So now you can choose, right? You can use this wire to choose, do I want to use input 0 to connect to the output, or do I want to choose to use input 1 to connect to the output? That is your choice. So now you have to choose carefully. In other words, should I take this path or should I take this path here? Which one seems to connect to the register bank? 0. Okay, very good. So this particular wire, which is the control wire, has a name. It's address MUX. So we go back here and say ADDR MUX should be a 0 because we are choosing input 0 of this multiplexer to connect to the output, which then connects to the address port of RAM. So far, so good. Okay. So now we click on this wire and go like, it is still not going straight into the register bank. It's going through a demultiplexer. So what do we do? What is a demultiplexer? It's also a switch, but how is it different from a multiplexer? One input and multiple output. Very good. Okay, so when we look at this particular multiplexer, it has got one input from the register bank, but it's got two possible outputs. Of the two outputs, we know which one we want. We want output 0. Okay, so that means the control wire of this demultiplexer, which is RO1DMX, register output 1 demultiplexer, needs to be 0. Very good. Okay, so now we go back to here and say RO, this is uppercase O, 1, demultiplexer needs to be 0. Okay, so now we track it all the way down to this wire, which is the output of the register bank. Oh, great. So we get it all the way back to the register bank, but I still need to be able to specify register B to specify the address, right? So what do? We go into the register bank. Okay, we right click on the register bank, and then we say, from here, how do we make sure that register output 1 is going to connect to register B? What do you think? Register output 1 is going to a multiplexer, and what is going into this particular multiplexer? The registers, right? We are already down to that level. So if I want register B to connect to register output 1 as an output pin, what should I do? It should be a 0, 1, but what should be specified as 0, 1? Register out 1 select. If you put a 0, 1 here, then it will make a path connecting register B, which is the input 1 of the multiplexer, to the output. Is that okay? So I think the name is the same on the main screen. So when you get back to here, it is this particular wire or this tunnel that we need to specify. It's register output 1 select. Okay, it's just abbreviated, but it basically is the same thing. So we go back to here and we say register output 1 select needs to be a 1. Or if you want to be very specific and say this is a 2-bit thing, then you say 0, 1 as a base 2 number, just so that we are aware of this is a multi-bit kind of specification. Are we good so far? So now we have made a connection from register B to the A port of RAM. We have configured the RAM to 1. We say that RAM, hey, I need you to pay attention. And 2, we are going to perform a read operation. And we have specified the address. So the other thing we also need to do now is to take the output of the RAM module and connect it to register D. Okay, so we go back to the picture. And this time we highlight the D port. And this is the wire that connects to the D port. So how do we wire this into the input of the register bank so that we can update register D? What comes pretty close to it? Don't you think this mux here comes pretty close? Yeah, okay. So in this case, it's which input do we need to connect to the output? Register 0 is the value, so RI mux should be a 0. Now this mux is a little bit special. It has an enable pin to it, so we also need to make sure enable is a 1, because otherwise it is actually not connected. So we have 2 bits to configure. We have RI mux being a 0 and RIEN being a 1. Are we doing okay so far with that? Okay. So we go back to our document here. We say register input select is, oh, that's not yet. We have this mux is a 0, RIEN EN is a 1 for register input enable is register input enable is a 1. Okay, so far so good. All right. So once we have done all of these, we have to look into the register bank again because we are not updating just any register. We're updating a specific register, which is register D. Okay? So now we have to look at register D. We look at the input of register D called the D port, and that terminology is consistent with the discussion of D flip-flop. Okay? So this is the input, and now we're asking, how do we connect this to that? That's the question. So what do you think? What do we need to, what configures that? 1 0 or 1 1, 1 1. But where do we specify that 1 1? Register input select. Okay, very good. So if we specify a 1 1 here, then we would connect this wire or this input pin. This pin is connected to every single one, but the enable is controlled by the decoder, which in return is specified by the register input select. Let me say that one more time. This pin, register input pin, is actually multi-dropped into the input of every single register. So that means every single register is actually hearing the same thing, but we can control which one is actually paying attention. So as you already know, and I was once a student, and we understand the difference between hearing and paying attention, right? So all the registers are hearing the same thing, but we can control which one is paying attention. That is controlled by this decoder. Which output of the decoder is a 1 is determined by two things. One is register input select, and the other one is whether the decoder is even enabled. Okay? So that means if I want register D to pay attention to the input, I need this enable to be on, and that turns out to be output 3 of the decoder. So that means the select of the decoder has to be a 1 1. So now we go back to the document here. We say RISEL, register input select needs to be a 3, but if you want to use binary number, it will be 1 1 in base 2. So I'm just going to emphasize that these are base 2 numbers. Is that okay? And then what do we need? Yes? So the difference between a decoder and a demux, the multiplexer, is a decoder has no input because it is only saying, oh, which output should be a 1. So you can kind of imagine that it has an input that is a constant 1. It kind of is doing just that. So a decoder is kind of a deformed demultiplexer, so to speak. All right. Well, this is it. Then we just wait for a rising clock, because the register won't change until you have a rising clock at the clock pin of the register, and then it will get updated.
Did you do a decoder enable?
Huh?
Did you put in the list decoder enable?
Decoder enable.
You said 2 pins, right?
Yes, so this connects to the same as the other tunnel. Okay, so when you look at this wire here, it connects to the same tunnel that we have already talked about. So this is the tunnel that we are talking about. So we have already set this one to a 1. So that one specifies both to enable the multiplexer from the outside of the register bank, but it also enables the decoder inside the register bank. So it serves two purposes using only one signal. Is that okay? Cool. Well, we have just talked about the LD instruction. This is what the LD instruction does. It uses one register to specify which part of RAM to address, and then use the output of RAM to update another register. So are we okay so far with this discussion? Okay. Question? Go into the register bank? The decoder has no name. It is just this component is the decoder.
Why do we need an enable
Because otherwise, one of the registers is always going to be selected. If you do not have an enable for this decoder, the decoder is always going to read the select and say, oh, which one do you want to be a 1? So that means one of these 4 registers is always going to be selected, which is not what I want. I want none of them to be selected unless I want to actually update one of them. Yep. Mm-hmm.
Does the top one say and then the other black one says EN? I'm only asking because it's kind of hard to see.
You mean here?
Decoder is.
The decoder? This is in EN, but that's just the name of the pin itself. Outside of this, it is called register input enable. So are we good with this process? So now you know one repertoire of the entire processor, which is the load instruction. Is that okay? So now the question is, so what do we need to do to specify that instruction? Okay, so that the processor knows, oh, you want to do this. You want to connect one of the registers to the address bus of the RAM, and you want to connect another register to the data port of RAM, and then you want to update one of those registers. So how do we tell the processor this is what we need? Okay, so for that discussion, we go back to here, and then we have to go back to the network drive for this class, and I think I might have closed every single one of those. Question? Oh, okay. I thought I saw a hand. All right. So I am going to right-click and open a new tab here. And then we go to the shared folder. Go to processor. There are 2 documents that are particularly useful. One is a little more concise than the other one. So I'm going to use the concise one. All right, so this is the opcode table. And with the opcode table, you can look up, the columns. So let me just quickly explain what the columns are representing. Column A, which you can see, they're all kind of like binary bit patterns. That is the actual opcode, okay, operation code that the processor understands. Okay, the processor only understands 0s and 1s. Okay, so when the processor sees that the instruction to execute is 01000101, then it knows this is what it needs to do. Is that okay? So, huh?
What does that mean then? Equals Z?
Well, we'll get to that later. Okay, for the most part, you should be able to understand. This is C syntax, by the way. Okay, it's a ternary operator syntax. Okay, but we're not quite there yet. Okay, so we're not going to be too concerned about it. So anyway, column A is called opcode. It is binary. Okay, so if you have to program a computer only using opcode, then you'll be spelling out 0s and 1s all day long, which is not very effective, even in assembly language programming. We don't want to spell out everything in 0s and 1s. So that is why we have column B. So column B is known as the mnemonics. Okay, each row, each binary code as an opcode has an equivalent mnemonic. Mnemonic MNEMONIC, mnemonic, okay, is basically just a short name for what the instruction does. Okay. Some of these can be cryptic, like JZI looks kind of cryptic. Some of these are not cryptic at all, like add. That's not cryptic at all. You kind of know what the processor is going to do, right? It's going to perform some addition operation, okay? So mnemonic is just that, okay? Mnemonic makes it easier for us to remember how to specify an opcode, okay? We understand mnemonics. The processor understands binary opcode. Somebody has to translate, right? So that turns out to be our assembler. Okay, so the assembler is what allows you to write your programs using mnemonic, which is easier to remember, easier to understand, and to translate that into binary opcode that the processor understands. So that's what that kind of strange spreadsheet was about. Remember the previous lab? You guys have to use an assembler. There was a spreadsheet. All that spreadsheet is going to do is to do that translation. Yes?
Is there a reason they don't expand the mnemonic to be a less cryptic keyword?
Say that one more time.
Is there a reason they don't use the mnemonic, they don't expand it to like a name that's more intuitive?
Because in the good old days, this is intuitive enough. And to a certain extent, that's tradition, okay? Yeah, so that's convention. So LD is load. So the question is, well, why don't we spell out the whole thing, right? LOAD, right? So as it turns out, it's really just a tradition. People just do not want to type a whole lot. So they just type the minimum to differentiate the instructions. I mean, if you look at jump, it makes even less sense, right? I mean, jump is JUMP, and the mnemonic is JMP. It's like, how much does it take to type that U? Not a whole lot, but it's conventional. So I could have made my assembly language to make use of like full words or even phrases or sentences, right? So instead of LD, I could have said copy from RAM to register. But then you'll be writing programs using that. Copy content from RAM to location to register over and over and over again. So the problem is each assembly instruction doesn't do much. You need a lot of assembly instructions to just do something useful. So when you use like a full phrase to describe one single opcode, then you'll be spending all your time typing. So that's an excuse of using like not so intuitive shortened form of words. Okay. So let's look up the instruction that we just talked about, okay, which is the LD instruction. Okay, so let's scroll down. I cannot remember where it is. This is ST, which is store. Oh, here we go. This is the LD instruction. So let's focus on just this one row here. Okay. So what does it say? Column D is the full description. Okay, column D is just a full description. It says load dereferenced, which is kind of cryptic, unless you have taken cisp310, because then you know what is dereference, right? So in order to dereference, you have to have a pointer, and then something is storing what the pointer is pointing to. So that's what column C is coming in handy, because the column D is using some description in English words, but it can be ambiguous and not really telling you exactly how it is done. Column C is using C syntax to tell you what that operation is actually doing. Okay? So in this case, if you look at column C, the first one, now these two are equivalent, okay? So you can choose one or the other one to understand what it's supposed to do. Let's pick the first one. X equals star Y. What does that do? We are dereferencing Y, okay? We are treating Y as a pointer. We go to the location pointed to by Y, grab that content, and then use it to overwrite X. Okay? Well, the other explanation is using RAM as an array. So we are looking at RAM as a huge array where we are using Y as the index. Whatever the element is at RAM, index Y, we store that to X. So they're pretty much doing the same thing. It's really just a preference. Would you like to look at RAM as quote unquote memory, and then we use address of the reference to talk about things, or do you want to look at RAM as an array? I personally prefer to look at RAM as memory because that's what it is. So my personal preference is the former, the X equals to star Y. But if you want to kind of make the adjustment, you can use the other one as well to help you understand what the operation does. Are we doing okay so far? Okay, then what can be X and what can be Y? I mean, how can we have X, X, Y, Y in column A? Okay, so X is a register, Y is also a register. Okay, how many registers do we have in the register bank? We got 4 of those, A, B, C, and D. Okay, so when you see X, Y in column B, that means X can be any one of X, A, B, C, D, and y can also be any one of A, B, C, D. That is the syntax of the assembly language. Cannot be anything else, okay? If you say, I really know exactly where I want to read, it is location 23. Can I use 23 inside the parentheses so that I can just go to that location and grab that content? The answer is no, okay? So when you see X, it means it has to be one of the 4 registers. If you see Y, it means it has to be one of the 4 registers. Next question, can they be the same? Yes, they can be the same. In other words, you can use register A for both, in which case it will first use register A to determine which location to read from in RAM, read that location, and then update register A again. Okay, it can be done. Okay, so if X can be ABCD and Y can be ABCD, then what about XXYY in column A? How many bits do you need to specify one of 4 things? You need 2 bits. That's why we got XX and YY. XX are 2 bits to specify the register for X. YY are the 2 bits to specify the register for Y. Is that okay? Okay, so if that is the case, for what we just did earlier, okay, so let's look up this slide here. And I'll slide it a little bit to the side so we can actually see both the opcode and this one here. So we are dealing with LD what and what. If I actually write the assembly instruction in mnemonics, what would I use as XX in this case, which is the register getting updated? What would I use? Which register is getting updated? I think line 6 says that. D, okay. And then how do I specify the second operand? B in parentheses, okay? It has to be in parentheses. Now, I could have written the assembly language that does not require the use of parentheses, but I don't want to do it because the parentheses emphasizes that B is dereferenced, okay? And there are only 2 instructions that will dereference a register. One is load and one is store, okay? So this is the syntax. What about the opcode? What about the opcode corresponding to this mnemonic? So this is the MENMONIC, mnemonic. And what about the opcode? If I want to write the opcode corresponding to this specific mnemonic, what would that look like? Sorry? 0111, that part has to be there, okay? And then what would replace XX? 1, yep, 11 would replace XX because XX is register D, okay? And what would replace YY? 01, that's right. So I only put in the space so that we can actually look at the different parts. So in reality, there are no spaces between these bits, okay? It's just that when we look at it, it's nice to break it up. So 0111 is the constant, okay? That part has to be there as the most significant 4 bits. The next 2 bits, 11, is actually specifying which register is getting updated. And the next 2 bits, 01 in this case, is specifying which register is going to specify the address in RAM in order to, so that we can read from that location. Are we good so far? All right. So this is the kind of the general idea of actual operation. Okay, so let me go back to, are we good here? Yep.
So we can have 2 to the power of 4 opcodes, right? 16.
You are correct. So this is a family of opcodes, okay? So when you look at some of these, it's not a family, and some are, we can scroll up a little bit later. But when you look at load, LD, it is a family of opcodes. There are 16 of them, you're correct. Because you have 4 registers to choose as X, 4 registers to choose as Y, and they are independent. And therefore you have 16 actual, individual opcodes.
Yeah, so what I wanted to ask is why do we have like 36 lines there?
Well, because some of these opcodes, there are slots that are still unused. So I was trying to make this processor as risky as possible. Okay, some of you are going like, risky as in not safe? No, risky with a C instead of a K. Okay, so what is, I'm taking a slight detour here because I think it's important to kind of go back to that idea that we have talked about already, but we didn't talk about it a whole lot, okay? So we are talking about RSCY, okay, risky, okay, to make it, something that makes use of the risk philosophy is risky, okay? Okay, but what does that mean, RISC? Okay, the Y is just my thing. Reduced instruction set computer, okay, which means we want the least number of mnemonics and opcodes. And this processor probably falls into that area, okay? It is not absolutely the most risk possible or the most reduced set possible, but it comes pretty close, okay? It comes close with practicality in mind. I mean, just the fact that we have the sign flag, the overflow flag, and the L flag to use in here means it's not absolutely the most reduced, because we could have just gone with the sign and the overflow, and then we use extra code to deal with the L flag. But that would, that would not be a good trade-off. We'll talk about that later. Okay. So we only got like 30 or so instructions, because some of these are just spaces, and the first part has a little bit of documentation. So we don't really have that many instructions. Okay, so getting back to the pine tree. Okay, so we have in pine. Yeah, go ahead. Huh? CISC?
Yeah.
So the only difference is reduced versus complex. So the Intel the Intel i3, i5, i7, that entire line of processor, they are complex instruction set computers. Because if you count the number of instructions, especially in 64-bit mode, the AMD instruction set, there are at least 300 or 400 instructions, as opposed to this processor, which may have like 22 or something like that. All right, so are we good so far? Kind of, okay. So a few other questions, okay? So let's step out. We are looking at pine needles right now. So let's step back and take a look at the pine tree. So with the pine tree, let's go back to Logisim. Okay, so ultimately, everything is dictated by the processor architecture, which is kind of like a maze, right? And what we want to do usually typically consists of, oh, I need to take the output of here, put it over here, and then I want to take the output off there, put it over here. That is what we want to accomplish with each instruction. So the first thing you need to do is to read this diagram, get familiarized with it, so that you know which component is where, and how each component may or may not be connected to another component through multiplexers and demultiplexers, okay? So this is the map of Solar Island. If you need references to what that is, refer to the previous lecture, okay? Do you need a flashback? No? You guys are too sick and tired of the Naruto style of storytelling? Let's have a flashback of a flashback of a flashback in the middle of a fight, right before the contact. Yeah. And then 16 episodes later, we continue. So we're not going to do another flashback. But this is a map, okay? This is a map. It shows you all the pathways, all the roads, all the switches where you have control over, okay? You can say, I want to connect this input to the other output, okay? So that is the control that the controller has, can deal with, okay? This is the type of thing you can do. So that specifies the lowest possible level of explanation of how the processor works, okay? So once you determine, oh, I need this to be here, that to be there, that to be there, then you have these things, okay? In other words, you are now specifying, which tunnel is going to have which value and so on. Okay, that is, look at this as the instruction sheet that Sir Topham Hatt has whenever he needs to go like, oh, how do we get more coal into storage, into the coal storage place. Okay, we need to set up this track, hook up that track over here, so that we have a rail connection between the coal mine and where we want to store coal. Okay, so that's basically the instruction sheet for the controller to follow and go like, oh, I need to flip these switches like this to get that accomplished. Okay. Then we have a disconnect, because now we move on to the mnemonic, which is a semi-easy or intuitive way to remember things, okay? And the underlying binary representation, which is this. We have a disconnect, okay? So this pine tree, something is wrong about this pine tree, because the two parts are not connecting. These bits here are not these bits over here. Something is missing, okay? These bits here, okay, which bit pattern I choose to implement LD, D in parentheses B is entirely up to me. I could have chosen any pattern. Any 8-bit pattern is fine, okay? That is arbitrary. These bits here are not arbitrary because they are controlling specific multiplexers, demultiplexers, enable lines of registers, and so on and so forth. They cannot be arbitrary. So now the question is, what is mapping this arbitrary bit pattern to these bit patterns that are not arbitrary because they depend on the actual architecture itself? So that missing piece is in the ROM. Okay? So now we look at the one last component, which is really essential to the operation of the processor. And in Logisim, it doesn't look big, but it's actually very important. This is the ROM. Okay? So the ROM, if you look at the ROM, the properties of the ROM, it has got some really weird setup. Okay? It has 12 address bits, which means there are 4,096 locations. And each location has 26 bits. That is really odd. It's not 8, not 16, not 32, not 64. It's just some really kind of oddball number. Okay? But why is it important? Well, let's go ahead and look up something here. So I'm just going to look up, so you can go to edit content and look it up. And I'm going to look up, let's see, 0111 is a 7, 1101 is a D. So we are looking at 7D. Now, let me backtrack, okay? Because some of you are thinking, what are you talking about? Now, if you're asking in your head, without saying out loud, what are you talking about? Good. That's what I'm expecting, okay? Instead of whatever. See, I can see 3 different responses, in class, okay? And of course, all the different shades of gray in between. One is, I get it, okay? I got this. Good, okay? The second one is, what is this? How does it connect to what you just said? That's good too. That means you're paying attention. And the third one is, whatever. That would not be good. And I can tell you, depending on which class I was taking when I was a student, I can be any one of those 3 in class. Not at the same time. Okay, so we are looking at this opcode here. 0111 as a hexadecimal digit is 7. You can make your own little lookup table, okay? And then we have 1101 here, and that is D. So we have 7D as a hexadecimal representation of these 8 bits, okay? So now we go in here, and then we try to look up 7D0, okay? There's a reason why it's padded with a 0, but I'll explain that later. So we look up 7D0, which is right here, okay? Then you go like, okay, fine, that's 1501076. What is that? Well, let's try to remember that. So we do a Control C, and then paste it back into here. Okay? And now we try to decode it. So I just copied a single location in ROM, okay? And I'm trying to break it back into bit patterns. So the 1 is easy. 1 is 1. And then the 5 is 0, 1, 0, 1. The 0 is 0, 0, 0, 0. The 1 is 0, 0, 0, 1. The 0 is 0, 0, 0, 0. And then the 7 is 0, 1, 1, 1. And then the 6 is 0, 1, 1, 0. So I'm just checking here. 1, 2, 3, 4, 5, 6 plus 1. Okay, 26 bits. Okay, so we got almost 26 bits. Put a 0 here. Now we have 26 bits. Okay, so now you ask, what are these 26 bits doing? Okay, let's switch. Okay, let's close this view because we have just copied the 1 byte that we need. And then we'll go to the bunch of tunnels that we have here. And I kind of want to display both at the same time. So let me change the size of my editor just a little bit so we can display that here and the number here. Okay, that's perfect. Okay, cool. So now we want to look at which bit is corresponding to which tunnel. Well, yep. Which one? You mean Logisim? Logisim? If I make it bigger, I may, well, let me see if I can reposition it a little bit. Yep, I can do that. Sure. And we still have to show this part here. And then the editor is over here. There we go. Okay. So let's count bits. Where is bit 0 going? It's right here. Bit 0 is going someplace back to the control part of the ROM stuff, okay? So let's just not pay attention to that. So we'll not pay attention to bit 0. What about this bit 1 here? This bit 1 is going to RAM cell. And it's a 1. Did we mention that we want RAM select to be a 1? Okay, all right, cool. Bit 2 is going to RAM load. Did we say that load of RAM should be a 1? Yeah, okay, good. Bit 2 is going to microcode data, which is somewhere back there. We'll deal with that later, okay? And then we have a whole bunch of bits going to the splitter, okay? So we have this entire thing. We have bits 3 to 23 going to the new code data, thing here, and then it got split up into further ones, okay? So what that means is bit 0 here is actually bit 3 over here. So let's do additional counting, right? So this is bit 3, which is corresponding to this 3 here. RIMUX. Did I specify RIMUX or the register input multiplexer to be a 0? Okay. Bit 4, RIEN, and that's bit 4 over here. Did I specify register input enable to be a 1? I mean, I can keep going like this, but you kind of get the point, right? What is the point? Yep. Exactly. Yep. So once we figure out how to configure the multiplexers, the enable, the select, and all kinds of stuff like that, we just put it into one huge long string of zeros and ones, okay? And then we put it into the ROM. Okay, so big deal, we store it into ROM, but what is the connecting piece? The connecting piece is the opcode with a 0 padded to the right-hand side is the index into ROM to find the bit pattern that will configure the processor to do what it is what the opcode is supposed to do. That's the last connecting piece that finishes the entire thing. So are we doing okay? Cool. All right.
What does Ecode stand for again?
Microcode. So microcode is, this ROM here is not accessible in software. So this is factory predetermined when the processor is manufactured. And it is called microcode because it is one level below opcode. Opcode is what you can specify as a programmer. Microcode is what the manufacturer, like Intel or AMD, has to predetermine inside the processor. So you have no control over the microcode, but you can specify opcode any way you want. One other way to look at this is you can look at opcode as macros. And the macros expand to microcode that is stored in ROM. It's basically a table to look up. Oh, we need to do a load operation. How do we configure the processor to get it done? And you actually can have up to 16 steps to perform one instruction, because I left that much space to specify microcode. Do we have any questions? Because this would be a good time to ask questions, because we got a few major pieces here.
So every bit is set at once?
Correct. So when this particular slice, I call this a slice, is addressed, then all of these bits will be simultaneously presented to all of these tunnels, all at the same time.
So the task is done by executing that?
Correct. So the task is done, well, okay, so that's a good question, because whenever you need to update a register or RAM, you need a rising edge. So nothing is done really until the rising edge happens. But when the rising edge happens, then everything, all the paths will be connected in the correct way. So that rising edge will be able to update register D, in this case, with whatever B is pointing to.
So it would be one clock pulse?
Yes. Correct. Yep.
So for each slot in the RAM, did
Uh-huh.
you manually do every single one of those yourself, or
What do you think?
honestly,
If I could do that, I would be able to finish grading the mid exam 2 of this class in 2 days. So the answer is no. I did not do it manually. Yes.
How does the processor know how quickly to run the clock?
Aha, that's a very good question. Okay, so you can increase the clock to make it go faster and faster and faster and faster, right? So the question is, how do we know where is the limit of running that clock, right? What is the highest frequency you can run that clock? Is that kind of what you're asking?
Or how does it even know how to run it at all?
It knows how to run it, but the frequency, let me just kind of address that question first. So to address the question of how fast we can run the processor, we are going to put our focus on the ALU. This is the ALU, okay? We talked about it last time. It has some fairly complex logic in the inside, okay? So without going into the details of how to configure the multiplexers and demultiplexers, we'll just say that there's a way to connect register output 0 to input 1. There's a way to connect register output 1 to input 2 of the ALU. So we can use 2 registers to specify the inputs into the ALU, okay? The output doesn't really have too many places to go. So the output of the ALU has to go through this multiplexer and then go back into the register bank. In other words, every time we perform an add, subtract, or any type of operation with the ALU, the result is always stored in one register. Is that okay? So how does that have anything to do with the clock rate thing? Well, do you guys remember why we use carry look ahead instead of carry ripple when we perform addition? Because it's faster, right? Okay. Well, it's faster, but it's still not instantaneous. In other words, even though we can reduce the number of stages of gates all the way down to 4 gates, 4 levels of propagational delay, it is still time. 4 times 2 nanoseconds is 8 nanoseconds, which is time, okay? So that means the moment the data arrives at the input, you have to wait 8 nanoseconds at least, because we still have multiplexers and demultiplexers in the inside, before the output reflects the actual correct result of the operation. Is that okay? That output in return gets into here, gets back into the register bank. The register is waiting for a rising edge to update. Is that okay? So that means your clock cycle, okay, cannot be faster than 8 nanoseconds. Because if you have a rising edge of less than 8 nanoseconds from the falling edge, then the ALU would not have enough time to finish the computation before the register says, okay, I'm updating. So that pretty much limits how fast you can clock a processor. Now, there are many tricks to speed that process up, okay? In addition to having carry look ahead instead of carry ripple and stuff like that. In modern processors, like the i5, i3, i7 processors, they actually have many ALUs per core. Okay, so if you just look at a simple i3 processor, it has 4 cores, okay? Each core has multiple integer ALUs, which means it can actually perform multiple integer arithmetic operations at the same time. That is why we can do superscalar, which means we can perform actually more than 1 calculations per clock, which is really cool. Yep.
Has this affected any like using new technology on old technology? Like I think there's like some like you find bugs in like old game why do I never have the word, but like the old DSs.
Okay.
The word. You, or like the switch where you can't plug in a USB 3 into it even though it fits because it overloads the switch. Do you have any examples of like, or do you know of any instances where like this like slow clock time being overloaded by?
I don't have any example of that, but related to that, okay, I can tell you, how timing is important. I'm trying to think of the name of that exploit. It's based on the timing in hardware. In other words, it's not a flaw in software. It is actually in hardware.
Meltdown inspector, is that?
Huh?
Meltdown inspector.
Meltdown and inspector. That's right. Okay, thank you. So if you look at Meltdown and Spectre, these are 2 exploits that are based on timing in hardware. Now, it is not based on timing as in, oh, it takes longer than a clock to complete something, so and that becomes the hack. It is based on which operation. It's based on the race condition. Okay, it's basically you have 2 things going on at the same time. The engineers assume that this operation always completes before this one, okay, which ensures a safe, operation. But the hackers found a way to trick the processor so that it is the other way around, and that creates a security issue. It exposes data that is not supposed to be. Okay, so for those of you who are interested in hardware-based exploits, you can read further into Meltdown and Spectre. They're related because they are kind of the same type of approach, but they are different in the sense that I think they affect different operating systems. Okay, very good, cool. So I think I just answered the question of how fast we can clock something, and then back to this picture. Okay. So this is where everything starts, okay? We have to, look into each instruction and actually at least understand, oh, this instruction is trying to make a path from here to here, and then from here back to here, and so on. And then we have to manually be able to look through all the multiplexers and demultiplexers and understand, oh, this multiplexer needs a select bit of 0, 1, and that one needs to have select bit of 2, and so on. Is that okay? Then the next level of operation has to do with this. Okay, so the first thing is to look at the processor map, figure out the zeros and ones, to configure the pathways. Once you have all those zeros and ones, determined, then you come up with something like this. Okay, you basically say, I need that to be enabled, I need that to be disabled, I need this to be a 0, 1, I need that to be a 0, that one to be a 1, and so on. So you specify all of those things. Then what you do is you combine all of those into a long string of zeros and ones. That becomes a single slice of microcode that configures the processor in a particular way to get a certain thing done. Okay? Now, if you do not mind entering that kind of bit pattern for your entire program, I suppose you can program that way. But that would not be very effective. Okay? So now, instead of specifying this huge long sequence of zeros and ones, and there may be multiple slices to get one thing done, so instead of looking at these, we just say that, let's make it smaller. Okay? And this part is arbitrary, okay? In other words, I could have chosen 1, 0, 0, 0, and then 1, 1, 0, 1 to mean the same thing. I just moved the item around in the ROM, okay? That's all I need to do. Yep?
What's the major difference between a register and a RAM?
A register lives inside here. RAM, did you say RAM or ROM?
Yeah, no RAM.
RAM, and RAM is over here. I do not see any similarity.
So, isn't both of them kind of memory kind of device?
Well, how about we look at a register from the perspective of what is presented to the input, and look at the RAM and see how they're different. Okay? Does a register have an address? No, it does not. Okay. Why? Because a register is an individual thing, whereas RAM it contains multiple locations. Is that okay? With a register, let's just pick a register here. Flags, okay, is a register. The input is D, the output is Q. Do we see a Q in RAM? No, because the D port serves both purposes. It is both the input and the output. Okay? Wait, if a port can be both the input and the output, don't we need something to switch it around depending on whether we're reading and writing? We got load here. Do we have a load with a register? No. Now, they do have some similarities. Select and enable, kind of the same thing, saying that pay attention, okay? We also have a clock here and a clock here, which means, hey, I'm not going to update until we have a rising edge clock. That part is the same. We have a 0 here and we have a clear here. That is also similar. When you first power up your processor, we rely on these signals to say everything becomes 0 first. So they do share some similarities, but they're also different. So if you have questions like that, my advice is to go to the help menu here and read the library reference of those specific components. If there's any questions after reading that, I'll be more than happy to answer those questions. Is that okay? Okay. All right, so where was I? Yep, okay. So get back to here. So this is the highlighted portion is kind of like the opcode. It's really a way to index into a sequence of these long bit patterns. Is that okay? It's kind of like a macro. But instead of remembering, 0, 1, 1, 1, 1, 1, 0, 1, it's easier to remember it is LD, D, and in parentheses B. Once you get used to it, it is actually not too hard, not too bad. So we have the highlighted portion is the opcode, and then this part here is the mnemonic, which makes it slightly easier to remember. Yes?
When you said the mnemonic, you said D is the reference. Where are you listing what address in RAM?
It's whatever register B has. So whatever register B has as its content at the time becomes the address. Yep. So are you guys good for a demonstration using exactly that instruction? Okay, let's do it. All right, so this is basically an exercise of how to use the tool chain, which you have already done using, in the previous lab. So let's go back here, go to my assembler window, which I have. I don't think I have it yet. Okay, let's open it. So there are two assemblers. For your homework assignment, you can use either one for now, but I'm going to use this one because this is the latest version. And if possible, I would use that one to iron out any potential bug that is still left over. Okay. So you go to the source tab, and column A is something that you can erase. Okay, but I'll be very careful to erase the content here. I'm just going to do a shift click and just press the delete key. So never delete the column itself or delete rows, okay? So if you do a row select here and then just right click and say delete a row, that would not be good because that's going to offset everything and things won't work anymore.
What about right clicking and clearing column? Not deleting column, but clear.
I have not tried that. I think that should be okay because it's just clearing the content of the column without shifting the cells around. Okay, so we're just going to put in one instruction here, LD, and if you have a typo like blah blah blah, okay, it's going to come back and say we have an error. We have a register X expected, register Y expected because it recognized the LD part of the instruction. If you do the blah blah blah, from the get-go, then it will tell you unknown mnemonic. We don't know what it is, okay? So it does do a certain level of syntax checking, okay, but it's not nearly as useful as a C compiler. If you specify the wrong thing, it will complain about it too. So if you say register E, which does not exist, okay, we'll see what it says about this. It says register X expected, register Y expected, but it doesn't say that E is not a valid character as a register. So you kind of have to know what you need to do to get it to work. So now I'm getting it correctly, and there are no errors anymore. So you have to pay attention because if you have an error, okay, let me just inject an error here. Okay, I'll just spill some errors here. If you have any errors and you go to the output tab. Okay, not the output, sorry. It's the RAM file tab here. And it will say there are errors. If you see there are errors here and you download this file, it's not going to be loaded into Logisim correctly. Logisim will bark and say, oh, this is not the right format. Okay, so this is intentional to make sure that a program that did not assemble would not be loaded correctly. Okay, so let me go back and fix that error. Go back to source. And there are two ways to fix an error. If this is something that you actually want to type, but it is not a part of the code, you can comment it out, // Okay. And so that should fix that problem. And now we go to RAM file. And does that look familiar to you? 7D? Yeah. Okay, so we go File, Download As. You can choose any one of these two, comma separated versus tab separated, both will work. So I'm just going to pick comma separated, and this is the LD instruction. So I just named the file ld.csv. Now we switch back to the assembler. We reset the processor first, okay? So it's always good to reset the simulation first. And also, it doesn't hurt to double check and make sure that simulation is enabled, because otherwise, nothing is going to happen when you are ready to run the program. So now we right-click on the RAM. We say load image, and it's called ld.csv from the temp folder, and it is now loaded. Are we good so far? Okay. So now we are ready to quote-unquote run the program, which is not going to be very interesting, because all registers are zeros. Okay, so you cannot really see the effect of this program running. Well, you can in a way because you will see 7D ending up in register D, but let's make it more interesting. So I'm going to register, location 0A, and make it a 7.3, okay? And then I want register B to point to this location. This is location 0A. So I'm going to pre-initialize my register to point to that location. So I'm going to here, go to register B, and change this to 0A. So now we have something to work on, okay? So the result of running this program should have the content at location 0A, which is 7.3, being loaded into register D. So register D should end up with a value of 7.3 after this instruction executes. Are we good so far? Okay. All right, so how does that work? Okay, because I have just explained the connection, but I haven't explained the mechanism by which things are mapped, right? So remember, this is one of those V8 engines, that is in clear plastic. You can actually get to see everything that it works, everything that makes it work, okay? So this is the very first slice, okay? Remember, all registers are always automatically reinitialized to 0, 0, 0. So this is the first slice. What is it telling us to do? It's telling us that RAM is selected. It's telling us that we should read from RAM. Now, if you know that RAM is selected and we are reading from RAM, you should automatically ask 2 additional questions. 1, who is specifying the address? 2, the content is going where? Okay, does that make sense? Okay, so now we look into that, we look up the map, and we go like, okay, who is specifying the address? Click on that, and you can see address mux is now a 1 because it's light green. So that means input 1 of this mux is connected to the output. Where is this coming from? It's coming from the program counter, PC. So the program counter controls which location of RAM has the instruction that we want to execute. So program counter obviously is very important in the execution of a program. It is not directly software accessible, but it is indirectly accessible in software. Okay, where is it going? We are reading RAM, so where is it going? So you track down the data line, okay? It goes everywhere. But then you need to look into registers that are enabled. So if you look into registers that are enabled, you find that the instruction register is enabled because it has got a light green going to its EN. So that means we are reading the current location pointed to by the program counter, and it's going into the register, instruction register here. So when I clock it, you should see the instruction register getting updated. So I'm going to do a single clock. I have to remember how to do single clock here. Tick once, which is Control T. Aha! So now the instruction register is updated to 7D, which is what we put into RAM, right? Okay. And then we scroll down a little bit to look at the ROM again. It has not moved location because this one is a falling edge sensitive kind of thing. This is the next location. So with this next location, what is getting updated? We see that the microcode pointer is getting updated, okay, because it has the enable being a 1, right? But how are we updating the microcode pointer? Track down the multiplexer, track down the select of the multiplexer. It's selecting input 0. So input 0 is here, okay? Input 0 is connected to the instruction tunnel, which is here. So we are now taking the content of the instruction register and use it as a part of what will become the new content of the microcode pointer. Why is it only a part of the new content of the microcode pointer? This is a what? It's a splitter, okay? So bit 4 to bit 11 comes from instruction as a tunnel. It's 8-bit wide. What about bit 0 to 3? Coming from a constant of 0. So this is why we have 7D 0. That last 0 comes from the constant that we are padding into here. Okay? So you can actually tell it because if you probe this line here, That's 7D0, okay? So on the next clock, Control T, you can see how the microcode pointer is now updated to 7D0, and then we end up here, okay? So what are we going to do here? Once again, RAM is selected, RAM is in read mode. Where are we reading it to, or who is specifying the address? So you want to track down the address. Now this is really tedious for me because I have to scroll around and pan, but when you have a larger screen, it's much easier to understand this operation. So the address line, once again, is going through a multiplexer, but this multiplexer now has a select of 0, which means it's coming from this line here. This is going in from a demultiplexer, but the select of the demultiplexer is also 0, which means this is the correct output, and it's coming out of the register bank, output 1 of the register bank. Is that okay? What are we doing with the data pin? The data pin goes all over the place, so we are looking at things that are enabled. This is enabled. So that means the data pin is going through the multiplexer. We know that it's going through this multiplexer because RI mux is a 0. We know the multiplexer is enabled, so it's going into the register bank. Right-click on the register bank. So now we can see the 7.3, which is the content at the location where register B is pointing to, is coming in as register input. We can also see that this decoder is now enabled, and register input select is 1-1. And that's why output 3 of the decoder is now a 1, which specifies register D is now enabled. Is that okay? Which means all it's waiting for is just a rising edge. Because the clock is low at this point, give it a rising edge, now it becomes 7.3 and is updated. So the LD instruction has just quote-unquote executed. So do we have any questions?
So how many clock edges did it take to set up?
That's a very good question. So it takes one, okay, let me kind of go back out a little bit here. And I'm going to reset the processor, but without resetting RAM. So I need to clock it one more time. This reset only applies to the processor, but not RAM. Okay. So it takes one clock to, this is what we call the fetch cycle. We are going to RAM to grab the instruction. It's called the fetch cycle. This one here is called a decode cycle. It looks at the instruction that we just got, and it tries to figure out where in this ROM is corresponding to that instruction. It's called a decode cycle. So that takes 2. And then the third one is the actual one that does anything actually useful. So it takes 3 cycles to get to the work that we need to do. And then the 4th cycle is to reset it back to here, so we are ready to grab the next instruction. So technically speaking, it takes 3 cycles to perform this instruction. And that's why, when you hear about processors that can perform just 1 instruction per clock, it is pretty good already. But now we can have instructions that can perform more than 1 instruction per clock, which is even more kind of like, just, amazing, It's not just the cores, it also has to do with multiple ALUs per core. So that you can, it's really complex because, the way the processor works, it looks at the incoming instructions and it has to schedule which ALU is going to do which calculation for which instruction and optimize it so that it will basically take the least amount of time to finish all the instructions. And it's all being done in hardware. So, so modern processors are very complex with a lot of optimization stuff. All right, so I'm done with the lecture. I'm going to open up the lab. And if you can just stay a little bit longer, I can give you the access code after I turn off the recording.